Over the years, we've used a lot of different tactics to teach my children about numbers. We've used counting beads, an abacus, calculators, number blocks, and number lines. One of my favorites is the book You Can Count on Monsters by Richard Evan Schwartz. In this book, each prime number is represented by a monster, and that monster has some trait expressing that number. For example, the number 2 has 2 eyes, 3 is a triangle, the number 5 is a 5-pointed star, 7 is a 7-sided shape. And other numbers, it's fun to try and figure out where in the monster is the number represented. So that's kind of the puzzle of the book. For example, the number 29 is made up of 29 points to its electrical look and feel. We have the number 23. So these are all interesting monsters expressed through prime numbers. Each composite number is then expressed as a number of monsters that make up its factors. So the prime numbers that make up its factors become an interaction of the monsters. So here we have a 2 with the 2 eyes and 2 3s, and here they are interacting. We have the 4 2s making up the number 16, a 3 and a 5, a 2 and a 7 with the 7 eating the 2. So there's a lot. It's a delightful little book, and I highly recommend it as a fun way for kids to visualize primes and composite numbers in a number of different ways. At the beginning of the book, the number 1 is unfortunately very sad because it doesn't get to be a prime or a composite number. But this is just another tool in our toolkit, educational toolkit for teaching kids about numbers and giving them different ways to visualize them. So my son started learning about prime numbers at school in his 5th grade class, and I thought it would be a great chance to teach him about an ancient algorithm for finding prime numbers called the sieve of Eratosthenes. And using this ancient algorithm, what you do is you decide the range for the number you're going to find. And in this case, we're going to go to the number 100. So n is going to equal 100. So what you do is for the array of numbers you have, you start at the lowest number. You circle that because that's prime. Then you knock out all numbers that are divisible by that number. So we're going to take out all the even numbers in our diagram, in our array. And then, once you've eliminated all of those, you then go to the next lowest number that hasn't been crossed out, the number 3. And special thanks to my son for pointing this out to me. He said the 3s, he noted, can be knocked out on diagonals. So we'll take out all the 3s, everything divisible by 3. We'll go on to the next lowest number, 5. And we take out everything remaining that's divisible by 5. And the next lowest number, which is, in this case, a 7. And we take out the numbers that are remaining for the number 7. And then, because the number 10 times 10 equals 100, we know we don't have to go past this because 10 times 7 is 70. Everything from here to here, everything below or equal to the square root of the number n that we're trying to, that's the end of our set, we know we've covered it because there can be nothing greater than that. And so everything that's left is a prime number. And when we were done, he was really excited because we had this cool artifact that he could then take to school and show off to his friends at school, showing this algorithm for finding prime numbers. So a while back, I was working on a number Mandela generator, and the idea was that you could enter a bunch of different specs and generate a number Mandela out of it. And one of the things I wanted to highlight the primes. And so you can see the prime numbers highlighted here and here, and to draw them out to see if there were any patterns for the prime numbers and where they were appearing. And going online, I found this prime number checker function. And what I did was each number I would check is prime, is n prime. And it's a great little, this is a great little, very short function. First thing it does is make sure n is a number. That's what this is nan, is it a number? Is it finite? Is it divisible by 1 without a remainder? That's what this percent sign is, a modulus. It checks to see if there's any remainder. And is it less than 2? If it isn't any of those things, return false. The next thing it does is it eliminates even numbers, which, as we saw in our application, in our algorithm, the sieve of Eratosthenes algorithm, the number 2 eliminates a lot of numbers. Also, eliminate numbers divisible by 3. So then it does the modulus 3 to see if that's equal to 0. If so, it's divisible by 3, and if so, it's divisible by 3. Now the m, we mentioned that in our sieve, going through the algorithm, we saw that there was no reason to go past the number 10 because the 10 is the square root of 100, and therefore anything above 10 is not going to be divisible by. So here it is. It gets the square root and puts that into this variable m. So we've eliminated even numbers and numbers divisible by 3. We're going to loop through every number between 5 and m, incrementing by 6 each loop. So every number between 5 and the square root of n, we're going to increment by 6 each loop because, again, we've eliminated 2 and 3. So we're going to start at 5, and then every loop we're going to add 6 and check to see if it's divisible by that. So it's a very clever algorithm. I just wanted to share this with you as an example of kind of a sieve of Eratosthenes in the wild. Now, one way we could make this even maybe more efficient, but maybe not more efficient, would be to have an array. And every time we find we could try sieving out anything that could be divisible by anything between our number and n. But maybe that could also end up being a little too complex or computationally heavy. Prime numbers are very useful from a cryptographic standpoint. Let's say I want to send a message out to a recipient, but all I have are bits, ones and zeros, beeps and boops, trues and falses. How do I clue the receiver of my message into the fact that this is a message and not just random noise? One clue we can provide them is the number of digits in our message. For example, let's say we have 1,679 bits in our message. Well, that's an interesting number because it's semi-prime, meaning it's the product of 2 prime numbers, and can only be the product of 2 prime numbers, in this case 23 and 73. That 23 and 73 can then become the height and width of our message. So here I've added line breaks after every 73rd character in the bit stream. It doesn't make a picture, but it does give us hints of a pattern. Adding a line break after every 23rd character reveals something that is very clearly intended as a message, and this particular transmission is known as the Arecibo message. It was sent from the Arecibo radio telescope in 1974 at a ceremony to mark the remodeling of the telescope, and was sent more as a demonstration than as an attempt to communicate with aliens. The cluster of stars it was aimed at are 25,000 light years away, meaning it will take that many years for the message to reach them. So finally, here's a fun little exercise you can do in sending a cryptographic message using prime numbers, or rather semi-prime numbers. Here I've created a string of just what looks like random characters, and this is my message. And with this message, I'm going to send my receiver the number 3,901. Now, is 3,901 prime or semi-prime, or what are the factors for that? So to find that out, I took our isPrime function, and instead of returning true or false, it's now going to return the factors that went in to making up that number if it's not a prime. Otherwise, it's going to return the word prime. So let's take that, and what we're going to do is we're going to throw it into a browser console. And now we've got our isPrime function. So for example, if we enter 4, we're going to get 2 times 2. If we enter 18, we're going to get 2 times 9. And if we enter 3,901, we're going to get 47 by 83. So I don't know. I happen to know which is the width and which is the height of this. The person who receives the message is going to have to play around with it. So we have 47 by 83. In this case, I happen to know that the number is going to be 83 columns. So let's go to column 83. Is that one right there? No, that's 411. Let's go to column 83. Well, 83. 83. And then we do this over and over and over again and break our image down. And what will happen is if the receiver gets the message and they break it up the right way, they'll get the following message in ASCII art. You are the best. And there's a lot of online applications you can use. In this case, I used an application that you can enter some text and choose a font, and it will generate this ASCII art for you. What you're going to have to do here is you're going to have to add white space to the end of each line to make it 83 long, and then you're going to have to add line breaks to the end to make it 47 long and 83 wide. You can also do this with other images. For example, there's a lot of ASCII art. There's places online you can take an image and upload it, and it will generate ASCII art. And what you can do is then convert this into a long string of what looks like gibberish by removing the line breaks and creating a long binary string, possibly binary, or in this case, we're using ASCII characters. And so you can hide a message in a long string and send the user the number, the semi-prime number, which they can then use to decode the string. So that's a fun exercise, just something else you can do with prime numbers as far as prime numbers in cryptography. So I hope you enjoyed this. Just a few little things you can do, fun things you can do with your kids, fun things you can do with your students, playing with primes and cryptography and algorithms, primes, and cryptography. All those things related, just a few fun little exercises and a book that you can play with. Thank you for tuning in.